Hey guys, I hope everybody had a good last week and you're all able to finish your Unit 8 test Part 1 and Part 2. We are now moving into Unit 9, which is our last unit, yay! And it is over confidence intervals. So it's a complete right turn away from hypothesis testing, and we're going to now start calculating and doing more algebraic work. So have you ever seen The Price is Right? If you haven't, basically they select people from the crowd and they're super excited to come down and they want them to estimate the cost of an item without going over. So the person who gets closest to the cost without going over has an opportunity to win some money in the game. So let me ask you, how much do you think a standard box of Cheerios is? Okay. Would you be more confident if the box of Cheerios, if I said the cost was somewhere between $2 and $5? How much more confident would you be if I said that the price was somewhere between $1 and $6? What about if I even said it was between $0 and $100? You would probably be 100% confident that it's in this margin. Maybe your percent confidence would go down as we started to get closer and closer to the actual value. So in case you're wondering, the true cost of standard box of Cheerios at Kroger is $2.79. So that leads us into what is actually a confidence interval. So a confidence interval is a range of values that could possibly contain the true parameter. In this case, a true parameter is a population value. So before, when we were talking about athletes, we talked about an ability. Now, when I talked about ability, I said that you can never truly determine the athlete's ability because we don't have infinite amount of chances. So we're finding a range of values that you could have a true parameter. In this case, I could calculate a true proportion, a true mean difference. So there's all different types of values that I can calculate and estimate what the true proportion or true parameter is. So you're calculating that interval from a sample. So that sample gives us a good idea of what the actual value is, but it might not tell me the most accurate amount because it's only something countable. It's not something that we can actually get from the entire population. So let's say that we claim that the true proportion of rainfall in April is somewhere between 0.20 and 0.50. So maybe I think that the actual value is 0.35, but I give myself a little bit of wiggle room on the left and the right because I don't want to be wrong. I want myself to have more confidence that it's inside that interval than whether just a yes or no answer. But this is only a claim, so we can never really truly identify that 0.35. We can only best estimate what it is with an interval. So let's say that a baseball player hits 100 out of 500 times. So this right here is a set of observational data. It's something that's collected from a sample. It's not the baseball player's whole population of hits of what he has done in his life and what he could do in his life. It's just one sample. So we can say that we think that he's going to hit 100 out of 500 times. So he's going to hit 20%. But is that necessarily true if we look at one game? So instead, we calculate an interval, and we say that his proportion of hits is somewhere between 0.15 and 0.25. Okay, so I think that it's somewhere between this range. If you're 0% confident, that means your range is going to be super, super small. So if I'm 0% confident, that means that I might think that the actual number is 0.20. But I'm not 100% confident that that could be it because I've only looked at 500 samples. Okay, so if I want to be 100% confident, my interval is going to be really, really big. And that means that I'm going to spread out my interval to be a lot bigger. And maybe I say that he even hits between 0 and 1. Well, of course that's true. I'm 100% confident that that's true because a proportion can't go over 1. So there are two ways that we can increase our chances of finding the true value. So a value that we think is the answer, but we want to be more sure by creating this interval. So the one way we can do is increase the sample size. So instead of looking at 500, maybe we'll look at 1,000. Maybe we'll look at 1,000,000. Another way is to increase the confidence level. So if I create a 50% confidence level, I might be within this range. My true parameter is somewhere around here. But if I want to be even more confident, let's say I want to be 75% confident, then my range is going to get bigger, and I'm going to be even more confident that my true value or my true parameter is inside that margin. So what is a confidence level? It's the amount of confidence that you have that the interval contains the true population value. So if I'm 50% confident, that means I'm 50% sure that that true value is in there. If I'm 75% confident, I'm 75% sure that that true value is in there. Now, one important question that I ask a lot on quizzes and tests is, what does it mean to be 95% confident? And 95% is usually the standard amount of confidence that you're going to calculate, but I can calculate any percentage, but 95 is usually the go-to. So if we were to calculate 95% confidence intervals many times, infinite amount of times would be perfect, but just many times, only 95% of them would be successful in containing the true value. So let's go back to the weather. We said that, I can't remember, it said that it was between 0.20 and 0.5. Okay, so it's somewhere between 0.20 and 0.25. So let's say I took a sample of last year's April rain, and that's how I got this interval. And then if I repeat that under a simulation, I might get that my proportion is somewhere within, my true parameter is somewhere between this interval. If I repeat it again, I could get completely different numbers. So every interval can be different, okay? And if I'm 95% confident, then the intervals that I actually calculate, 95% of them will be right. So this one might not have the true parameter inside of it. Maybe the true parameter is 0.21, but these two do have it. So 95% would be correct in actually attaining the true parameter. So there's actually an additional video in the next slide, or in the next page in It's Learning, and it's talking about gumballs, and it really is a cool simulation on showing what 95% confidence is. So check that out when you get a chance. So another type of question that I typically ask is, how do we interpret a confidence interval? And anytime you actually calculate a confidence interval, you have to be able to interpret it. So this sentence should be pretty locked down in your brains. So Ryan Miller was the goalie for the United States hockey team in the 2010 Winter Olympics. He also played for the Buffalo Sabres. So as a goalie, his main objective was to prevent goals from the opposing team. So he wanted to save as many goals as he can. So let's say we calculate a 95% confidence interval for Miller's true proportion of saves in 2009-2010, and we calculate that interval to be 0.918 to 0.940. That's a pretty high save percentage, so he's pretty good. So notice that I wrote the interval in a different way. So in words, I can say a number to another number. But when we actually talk about a confidence interval and calculate it, you want to use brackets separated by a comma, with the lower boundary on the left and the upper boundary on the right. Okay, so this is kind of the format that you're going to use for interpreting the confidence interval. So the first thing is you talk about what percent your confidence level is. So the bottom part is your confidence level. So it says we are 95% confident, so we are 95% confident that the interval of plausible values, so that just means the possible values within the interval, from 0.918 to 0.940, that always comes from your interval, contains, and then you want to talk about your subject. So in this case, we're talking about Miller's true, and instead of parameter, I'm actually going to scratch this out because I want to talk as true proportion. So I want to be even more specific than just saying a parameter. So it's true proportion, and then to do what? So I want to say in context, what is he actually doing? What are we actually talking about? Oh, pen's acting up. Okay, so in context. So the context of this one is actually to save goals in 2009, 2010. And you want to be as specific as possible whenever you interpret. So the entire thing as a whole, we're 95% confident that the interval of plausible values from 0.918 to 0.940 contains Miller's true proportion to saved goals in 2009 to 2010. So over the next few weeks, we're going to look at 5 different true parameters: the single proportion, the single mean, mean difference, 2 proportions, and 2 means. And there's 5 different formulas that you can use to calculate the confidence intervals. All right, I hope you have a good Monday.